just use the matrix. Okay. So first, we can see that there is the tuple E denoted as E, or maybe we also can say this is the vector. Yes. E means it existing. It means the number of resources. For example, there are four types of resources: tape drivers, plotters, scanners, and CD-ROMs. Yes, 4 types. Okay. And the number of tape drivers is 4. Yes. The number of the second resource is 2. The number of the third resource is 3. Yes. The last one is 1. Okay. So this tuple tells the types of resources and each type how many. Yes. We have 4 types and each type the number. Okay. This is the first one. The second one is available resources. Yes, A means available. Also, 4 types of resources, and now the available tape drivers is 2. The number is 2. Okay. We can see that there is a matrix. This matrix is the current allocation matrix. So it means that some resources have been allocated. Okay, each line, or maybe we can say each row is a process. So how many processes in here? How many processes? Each row is a process. Yes, 3. Okay. Process 1, process 2, process 3. Yes. Okay. So each column denotes a resource. Okay. So the first column denotes the resource tape drivers. Okay. The second column is plotters. The third one is scanners. The final is CD-ROMs. So we just focus on the first row. The first row means that the first process is now gets gets 1 scanner. Okay. There are total 3 scanners, and 1 is allocated to process the first process, or maybe you can say process A. Okay. Next, we focus on the second row, process B. So this value means that process B gets 2. Yes, good. Tape drivers. Yes, and 1. Yes, CD-ROMs. Okay. The third row is another process, process C. Process C gets 1 plotter and 2 scanners. Okay. The last matrix R means request. The first capital. Yes. Request. Also 3 process A, process B, process C. They are the same process. Okay. Process A requests 2 tape drivers. Okay. And 1 CD-ROMs. So we can see that process A gets 1 scanner, but it requests 2 tape drivers and 1 CD-ROM. Okay. about process B. The last row is about process C. Okay, so we can see that two matrices, current allocation matrix and the request matrix, two matrices. Okay, we just return back. We just use denotions, yes, not numbers, just denotions. So the first, this tuple in the resources in existence. Number, yes. Okay. And each column is the type of resource. Okay. This is the number of this type of resources. And this tuple is available resources. So this is the number of available resources. The first type, yes. Okay. So we can see that there are n items. There are also n items in the tuple. Yes, because n means the number of the type of the resources. Okay. For example, in this is the number. There are 4 types. So n is 4. Yes. Okay. 2 matrices, C matrix, R matrix. So this is the same. The ith row means the ith process, and the jth column means the jth resource. Okay, that's great. So we will find that there are some equations about these denotions. For example, if we summarize each column in the C matrix, summarize each column. For example, the first column we summarize C11, C21, and so on until Cn1. So this is the summarization. Is the number of allocated resources. Yes. Maybe I can write down the equation. For the JIS type of resources and the
number of process is summation.
This is C and J. We just summarize these values.
Yeah.
And each value means the number of allocated resources for a process.
Yeah.
For example, this one means how many resources are allocated to process 1 for the resource 2, yes?
Yeah.
So we summarize this column, and the value is how many resources are allocated.
Allocated in
Yes, for the JIS type of resource. For example, if we summarize the first column, 0 plus 2 plus 0, it means how many tape drivers have been allocated. Yes, the first one means how many has been allocated for process A, how many has been allocated for process B, C, and so on. If we summarize each column, so it means how many of tape drivers have been allocated. Yes. Is there any problem? No. Yes. Okay. So we come back. So this one means how many the JIS resources
have allocated in the
allocated. Yes. For all the processes. Yeah. Okay. Now we know that AJ means the available resources. Yes, the number of available resources for the J resources. Available J resources. Then we summarize these two values.
Then we can get
this is allocated. This is not allocated. And so this one is
existing.
Total. Yes. Existence.
Resources.
Okay. So why we got this equation? Okay, that's correct. We just continue the demo. So we will find that the summarization is 2. 2 plus 2 is equal to 4. Okay, this is 1 plus 1 is equal to 2. So we also can say that if we are given the E tuple and the C matrix, we can compute A. Yes, we can compute A. Okay. Okay. Now let's focus on available tuple and the request matrix. Now we first focus on the first law. The first law means that process A requests 2 tape drivers and 1 CD-ROMs. We just compare the first law with A. 2 tape drivers and 1 CD-ROMs. We can know that there are 2 tape drivers available. So this request can be satisfied. Yes. Yes. But this one.
But there are no CD-ROMs.
Yes, there are no CD-ROMs. So this request can't be satisfied. Okay. Then we focus on the second law. We will find that we also can satisfy process B. Third one, process C. Can we satisfy the request?
Floaters, one floaters available.
Yes, satisfied. Yes, there are 2. This value is much smaller than this one. Yes, 1. It means that process C can run and finish its task. Okay. So if I given you the tuple E and the matrix C and the R, first we can compute the tuple A. Yes, using this equation, and then I want to find a location without a data locker. How to do the allocation? It means how to allocate the available resources.
If they are, we see their request.
Yes, compare request.
Yeah. If they are available, then we can satisfy.
We just
then we can allocate it.
Yes, we just run this process. Okay, let's continue. We have allowed that process C can run. Yes, because two tape drivers and one plotter are satisfied. Okay, so we just run process C. Then after the process C finishes the task, we just release. Okay, so it means that the available tuple and the request matrix change. Okay, we first focus on R. R now becomes first two rows because process C is task. But we should notice that process C will release its resources. So A just change. So can you tell me the value about A? Can you tell me? After process C released its resources, can you tell me the value about the tuple A?
10 members 2.
The first one is 2.
Yeah.
Okay, the second one.
Floaters also 2.
The second one is also 2.
Then scanners also 2.
This third one is also 2.
Then
the last
0.
one.
0.
Yes, correct. Because process C releases its
all resources.
Yes, so these resources will also be released. We just add these rows to the origin A. Okay, so we can see that 1 plus 1 is 2. 2 plus 0 is 2. So tuple A becomes 2, 2, 2, 0. Okay, so now continue. Continue this one. This is the available tuple. This is the request matrix.
Now process B we can satisfy.
Which one can be satisfied?
Process B.
Yes.
The second
Process B can be satisfied.
Yeah.
Okay, because this request one tape driver and one scanner just is satisfied. The value is smaller or equal to this one available resources. So it means process B runs and then finish its task and release the resources. So the next one, this R matrix change. Okay, we can brush this row only one row. Okay, and we just change the available tuple. So tell me the new value.
is 4.
The first one is
10 drivers with 4.
yes. This one is 4, and then The second one doesn't change.
Yeah.
Doesn't change. And the last one
is 1.
Okay, great. The last one is great. Is 1 because these resources will be released. Okay, so we just add corresponding values to QA. Okay, return back to the request matrix and the available tuple. We can see that now process A will be satisfied. So we just then run process A and release its resources. So we will find that there is no deadlock. Okay, there is a location such that no deadlock. Okay, we come back to this algorithm. This is the algorithm which summarizes our ideal. The first step is to look for unmarked market process such that the ith row is less than or equal to A. So it means that we want to find a process whose condition will be satisfied. Okay? This is why we choose process C, because process C is satisfied. Yes? Okay. And then we just run the process and release its resources. So the available tuple changes. Okay. And there is a loop. The next one is also look for a process satisfied and release its resources and so on until we will find that no such process exists. Yes, we can't find a process such that its condition can be satisfied. Okay, so this is the algorithm. Okay, I think it is very easy and it is more simple than this one. Yes, than the depth-first searching algorithm. Okay, it is much simple. We can see that we two resources to process B. And now process B has 4 resources. Okay, so the available is 1. Then process B finish the task and release the resources. Yes. So has there no? The matrix is now because process B has finished the task, but 4 resources is released. So the available resources is the number is 5. Okay. Next one we will allocate the 5 resources to process A or C.
C.
Yes, because C already placed 5.
They are available also 5.
Yes, there are already 5. But the process A requested 6. Not so many. So we allocate these 5 resources to process C. And then process C finish the tasks and released. Okay, so becomes there no and now, and the available is safer.
Now we can satisfy
Yes.
process A.
Yes, we can allocate 6 resources to process A. Okay, you will find that this allocation will enable each process to finish its task. Okay, so this is why we call the state is safe. This one is safe, this state is safe, and so on are safe. Okay. But maybe sometimes there are unsafe states. For example, continuous example, the initial state is safe. I mean, this matrix is the same with this one. The initial state is safe, and but we make allocation in another way. For example, there are 3 available resources. Okay, and we allocate 1 resource for process A. So process A now has 4 processes, and the available processes is 2. Yes. Okay. And the next one, we will find that process B requires 2 processes. Yes. So we just allocate these 2 resources to process B. Then process B can finish tasks and release the resources. Okay, so there are 4 resources, and we will find that can process A finish its task? No, because process A requires 5, but we only have 4. Similarly, process C requires 5, but we only have 4. Yes? Okay, so we can see that this state is unsafe. The first one is safe because
all are
yes.
satisfied.
Yeah, the first one is safe because there is an allocation such that each process can finish the task. But the second state is not safe because there is no allocation. Okay, maybe you think you can allocate these two processes, and you will find that none of the 3 processes can finish the task. You can find an allocation such that each process will got enough resources. Yes. So this is why we say that same. We first find a process such that it can be satisfied. Yes. We find a process such that can be satisfied. And then this process run, finishes task, and release the resource. Okay, so we will just continue the step. We find a lot of process can be satisfied. Yes, and so on. This is the simple idea. We have known this idea in the example. Yes, this is simple. In this example, there are 10 resources, and one for A, one for process B, two for process C, four for process D. Then only 2 resources are available. Maybe we allocate 1 resource for process B. So process B now has 2 resources, and only 1 resource is available. And we will find that this state is not safe, because no matter you allocate this resource to process A or
No.
Yes.
Any process is not satisfied.
Yes, no process satisfied. So why this state is not safe? Okay. This example is for a single resource. Maybe there are multiple resources. So this one is the same. Example: tape drivers, plotters, printers, CD ROMs. Yes, multiple resources. Okay. So the idea is the same. We just want to find a law. A law means a process. Yes, we want to find a law such that it can be satisfied, and then this process gets the resource, conduct the task, and release the resource, and then we find the next process satisfied, and so on until we can't find a process satisfied. If there is a process there is a process such that you can be satisfied. There is a deadlock. Yes. Otherwise, we got a allocation such that each process will be satisfied. Yes. Okay. The idea is simple. Find one satisfied, and then release the resource, then find another, and so on. Iteratively conduct this step. Maybe we can also say that there is a loop. Okay. Oh, okay.
And then the next pass through, suddenly I'll notice that T1 and T3 can run. I'll run those, everything will be done, I'll be good, there'll be nobody left when I'm done, and now I have no demo. Okay? Now, is this reality? So what's a little, not perfect about this algorithm? Yeah. Yeah, so the assumption here is that T2 really will run correctly to completion. It's not easy computing.
If I use this figure as an example in the combination. I think you can find the loop, yes?
Yeah.
It is simple, okay? Okay, that's good.
Teaching 5, your last division 5, and not giving up its it will give up its resources at the end. So this deadlock detection algorithm is really only detecting for cycles under the assumption that the threads will behave correctly. Okay? All right. Questions? Now, what to do when you detect the thread as deadlock? We already sort of talked about this, but you can terminate the thread and force it to give up resources. This is the bridge example of Godzilla tosses a car that's giving up resources, and now you can shoot a diving wire. I guess that's not a good idea. So basically, killing the thread and holding the mutex leaves the world inconsistent. So basically, these scenarios are not a good one. Okay, these do not usually do the right thing. In the case of preempting your resource without killing off a thread, that often doesn't fit with the semantics of computation. And then you can roll back. And I mentioned this earlier, that's what databases do. So basically, once you're in a deadlock, the only way to get out of it is to get rid of one of the threads. And that's kind of, you got to think about what that means. And clearly, rebooting is the best example of terminating all the threads and starting from scratch. Right? Okay. So, let's take a break, and then I want to talk about techniques for preventing deadlock. So, everybody, 3 minutes. Deadlock. And I wanted to mention that one technique for preventing deadlock is infinite resources. Which, if you think about it, if you have enough resources, nobody's ever going to get into deadlock, because that cycle requires you to you're trying to acquire a resource that's in short supply. Otherwise, you're not going to get a deadlock. And this is a little bit over the top, right? Baybridge with 12,000 lanes, you never wait. But if you think about it, there's a lot of times when you can virtualize resources and make them effectively infinite, like lots of storage or whatever, and thereby get out of cycles that might otherwise occur. You might avoid sharing entirely. If you have no sharing of resources, no deadlock. I don't have to convince you all of that, right? Because you have at least 2 threads sharing the same resource. And the other is to prevent waiting. So all I'm doing, by the way, here is, remember I have those 4 conditions for deadlock? Those necessary but not sufficient conditions. If you remove any one of them, you can't get a deadlock. So for instance, if you never wait, there will be no deadlock. And so this actually is how it's helpful now that our phone company avoids deadlock. If you ever call and get a busy signal, and I actually, even you can still get busy signals. They're not as common, but they happen. That can reflect a lot of things, including the fact that there is no path that's free to the destination, in which case what they do is they just drop your call and they assume that you're going to retry it. No deadlock there. Okay, there's a lot of paths. You might never get through to your mom, and maybe that's pretty unfortunate, but you have to tell her you don't want to do it. But basically, that's a way of avoiding deadlock. So Ethernet also avoids deadlocks by dropping packets. And a lot of networks drop packets. So when you send a packet from, and we'll talk more about networking later in the term, but when you send a packet from here to Beijing, if there's some place that doesn't have enough resources, they don't risk an actual deadlock. They just drop the packet and assume you'll retry it to the source. Okay, so getting rid of waiting is a valid way of getting rid of deadlock, and you're trading off the potential for blind walk, the potential to never make forward progress, but nobody will ever be in deadlock. And this is a valid choice. Okay, so we're assuming that you're not doing that right now. The other possibility possibility that's kind of an interesting one. Now think about this. You can have all threads request everything they need at the beginning. If you request everything you need, then you either get it all or you don't, and you wait. And once you've got it all, nobody's waiting on you because you'll get all your resources, you'll go all the way through and you'll release your resources and there's no deadlock cycle. Okay, because if you look at all the cycles I've shown you up till now, they have a situation where a thread grabs one resource and held on to.
That's all for this lesson.